finally got AI-generated hair, fully working in Blender. Starting from just a single photo, it instantly generates 100,000 strands of hair and imports them completely into Blender, fully editable, adjustable, and compatible with geometry nodes. Hello everyone, I'm Fanfan.
I'm Xiaoyao.
Alright, today we're going to talk about AI-generated hair. Nowadays, AI has almost permeated every aspect of 3D production, from 3D characters to scene creation, and even skeletal animation now involves AI-powered 3D tools. But there is one thing that few people have really explored: hair. I've spent some time researching this problem, and today I'll share every detail of my end-to-end workflow, including all the pitfalls I encountered and the solutions I designed. Alright, let's first understand why this problem is so challenging. Why, up until now, has AI-generated hair seen so little adoption? We can actually approach this question from two angles. One is technical, and the other is practical implementation. First, let's talk about the technical side. For example, if you take a photo, the AI can see your hair from the front, but what about the back of your head? That part is invisible. Another case involves short hairstyles, where parts of the hair overlap and obscure each other, which the AI might also struggle to interpret. Take a look at these images. These are some methods published by academia, output in scenarios with extremely curly hair and baldness. It essentially just fails outright. This is the issue with AI 1.0's discriminative approach. You can't see it, so it is hard to imagine. That is the first layer of the problem, but fortunately, we now enter the era of AI 2.0 with diffusion models and stable diffusion. Various generative approaches have emerged, so this problem now feels solvable. So let's assume we find a research paper that technically solves the hair generation problem. And then
it is just a matter of implementation.
Yes, on average, a person has about 100,000 strands of hair.
Is there scientific evidence for that?
Yes. So those 100,000 strands of hair, each strand is a line. And what makes up a line?
A line is made up of points.
Exactly. The denser the points, the more accurately we can describe the shape of the line. For a single strand of hair, we use 256 points to describe its shape. And each point has 3D coordinates, so it has 3 values x, y, and z. Then ultimately, our hair can be represented using a matrix of size
100,000 by 256 by 3,
which describes the generated hair in this way. In academic terms, we focus on how closely the hair I generate, but in 3D creation, we need it to first be lightweight enough so I can comb it, and also renderable. Plus, it must conform well to our model's head shape, because as we know, no two people's heads are exactly the same. So there's actually a gap between academic outputs and real character production. It's a significant divide. Well, as for me, I'm going to bridge that gap in this video. First, let's talk about which paper we've chosen. Actually, starting from 2025, alongside the diffusion models, the academic community has published some papers to tackle this problem. For example, in 2025, papers named Tangled and DiffLocks were released. Then in 2026, a paper called Hair Rabbit was published, but it takes a multi-view approach, generating hair from multiple angles. The reason I chose the DiffLocks paper is because it's open source and runnable locally, and currently offers the best results among open source papers. Remember those hairstyles that broke previous methods, like extremely curly hair and short hair like this? This is DiffLocks' output under the same conditions. Hey, the result looks pretty good, right? What is his core idea? He completely changes the way the problem is represented. Instead of trying to reconstruct from 2D images, mesh-based hair, he chooses to work directly in hair strand space to learn a generative model. But if he wants to train a generative model in this hair strand space, you absolutely need this data. This is actually another core challenge, because there is no real 3D hair data available. As we've seen, many 3D generation approaches, including mesh-based ones, already exist. And in 3D animation and 3D games, we already have plenty of such data. But for hair data itself, there is still very little. So that is one of the main challenges. The authors of this paper did exactly this. They synthesized a training dataset of 40,000 hairstyles in Blender, with each hairstyle containing about 100,000 strands of hair. They trained a diffusion model on this dataset. Alright, so far, everything seems perfect. We just need to get it running. And it looks like we're on the fast track to AI-generated hair. But unfortunately, that is not the case. This was the first pitfall we encountered. The official code only supports Linux. To be more specific, there are two core CUDA extensions for which no precompiled packages exist on Windows. If you try pip install directly, it just throws an error. But unfortunately, I'm a Windows user. I believe many people doing rendering like this are on Windows because we rely on NVIDIA GPUs to handle a lot of rendering tasks. So that is a really tricky point. We tried several different solutions, but each time there were new errors for different reasons. Anyway, we reached the conclusion installing this on Windows just fails. But what if I don't have a Linux system? There is an even simpler solution, WSL Windows Subsystem for Linux. You can install a Linux subsystem right on Windows. But here is something important to note. Even when using WSL, there are several critical versions that must align precisely. But nowadays, AI can help with this. If you have Codex or Cursor or Cloud Code, installation becomes very straightforward. Alright, after all this trouble, the moment it finally runs looks like this. Not bad. It already smells delicious. But between the generated data and actual production, a second problem emerged. Let's look at DiffLocks. Its output contains roughly 100,000 hair strands, each with 256 3D coordinate points. As for hair think weight, the roots have some basic predefined root positions. In the DiffLocks paper, the root positions are by default based on SMPL, an open-source human body model to calculate head geometry. The hair is also designed for this standard head model, but of course we won't actually use this standard head. We have our own character. Between your character and this hair, it is essentially like wearing an ill-fitting wig. The overall shape is there, but the hair roots are completely misaligned. So we definitely need to readjust it to make this wig truly belong to our character. The first time I tried this, I directly used the raw data to handle the issue. Just to note, this raw data is about 139 megabytes, quite large. My machine has an NVIDIA RTX 4070 Ti Super. As you can see, we've imported this hair into the project. After some simple adjustments, it barely fits onto my character's head. It doesn't fit well, so we still need to tweak it further. First, we need to snap this hair onto our character's head. This method is very simple. We just click on the hair, then click on the head to snap it into place. But there is an issue here, since some of these hair strands might be too far from my head mesh. Some curves can't find their correct snapping positions, so some curves aren't actually snapped onto my character's head. It is hard to adjust the roots in that state. The next issue after snapping it onto the head, I'll definitely need to fine-tune it a bit. We can see that even basic grooming already causes severe lag with the brush strokes. But once you try to move the root position of your hair, for example, if I want to adjust my hairline, it just freezes completely. And it is also related to the length of your hair. The longer your hair, the more it lags. It becomes completely unresponsive. Just imagine this, 100,000 strands of hair, each with 256 points on it. Even high-end GPUs can't handle this during interactive editing, let alone ordinary laptops, which might not even manage basic grooming. That is the problem, right? This is totally unusable. It is still the same issue. If it doesn't actually work in real 3D creation, what is the point of loading it in if you can't use it? Then what is the solution here? It is double downsampling. First, we reduce the number of hair strands from 100,000 to 1,000. In this case, we achieve a massive reduction. The second downsampling is applied to the points along each strand, reducing them from 256 points down to 50. How few points can we go down to at most?
2 points.
Right, because 2 points define a straight line. Of course, for extremely curly hair, to preserve its shape, we'd better keep all 256 points initially. After downsampling and attaching it back to the scalp, it becomes incredibly smooth. We can freely style it in any way we want, whether it is adjusting the hairstyle or the roots. Let's see what kind of qualitative leap. Our file size went from 139 megabytes straight down to 1.39 megabytes. And our loading time used to be 0.13 seconds for the 139 megabytes file, but now it is only 0.002 seconds to load it in. Previously, the whole grooming process would just freeze. Now it is incredibly smooth, great, super fluid. These 1,000 strands essentially serve as guide curves for your hair. If I later want to go back to 100,000 strands, I can just upsample it. I just add this duplicate geometry node and directly upsample it, bringing it back to nearly the original result. And this step is fast with great results without losing a single strand of hair. Pretty impressive, right? Let's briefly talk about why DiffLocks can achieve this. The core of this method is actually that it changes the representation. Hair is inherently linear by nature. It consists of individual hair curves. It is not surfaces, nor volumes. Because most current AI 3D generation models, they're all designed to handle mesh-based data structures, but hair strands are actually quite special. So DiffLocks actually models directly in hair strand space. That is its model architecture. It is actually similar to standard diffusion models. It first designs a VAE that can encode hair strand shapes into a latent space. Then its diffusion model operates within this latent space, conditioned on hair texture to regenerate the full hairstyle distribution. Finally, it decodes back into real-world coordinates. Here's a very key insight. Diffusion models are generative models, so they can avoid some of the issues we had with previous discriminative models. But they also have their own limitations. In my actual testing, I found that when the input photo is close to the typical frontal portrait distribution used during training, the results are quite good. But in reality, it shows some tendency to overfit this data. For example, if I use images downloaded from Xiaohongshu to generate hair, the results aren't as good. In other words, for photos with more complex lighting or larger viewing angles, what we call wild photos, the quality of the generated hair strands falls short of my expectations. Additionally, this model currently doesn't support braids, hair accessories, ponytails, buns, or any tied-up hairstyles. All styles with accessories, they still require manual work. So here is our conclusion. It is currently a usable tool, but it can't perfectly handle just any photo with a single click. Now, hair is widely recognized as the most challenging part of 3D characters. We've now established a pipeline that goes from a single image to editable and character-fitting hair, ready for final rendering with 100,000 strands. Alright, this is the first episode of our series on building a complete character pipeline using AI. In the next episode, we plan to use AI to generate clothing, or perhaps migrate this AI-generated hair from Blender into Godot. We'll see how it performs in a game environment. But all of this is within our planned scope. It'll depend on how I'm feeling for the next episode.
Can this DiffLocks be used commercially?
No, not for commercial use. Academic use is allowed. If you like to use it commercially, you can contact their team to obtain a commercial license. If you found this helpful, please consider subscribing to our channel. See you in the next episode. Bye!
Bye.